Good afternoon to everyone. My name is Soulioti and I am Project Manager at MTech Space PC. I will present to you ACOSIM, an ESA TRP study related to the application of cost simulation in support of tests and operations. First, some background information for the project. ACOSIM is an ESA ESTEC initiative within the Basic Technology and Research Program. It started in 2018 with 2 years planned duration and €600,000 total consortium budget. The project is executed by 4 partners. MTech is leading the consortium, having as its subcontractors Thalys Alenia Space from Italy, TVT from Germany, and the Aarhus University from Denmark. The main objective of the activity is the analysis and application of new simulation technologies and frameworks, and in particular FMI and cost simulation, as enabling technology for the system-level simulation in support of verification, validation, and operations of a space system. In other words, how can the concepts and technologies of FMI and cost simulation improve the current processes, taking also into account the lessons learned from previous space studies? Another objective of the project was also to promote both vertical and horizontal reuse of simulation models. Very shortly from the beginning of the project, it became apparent that in order to achieve these objectives, not only the source code of a model is important, but also the complete life cycle data needs to be considered to make reuse truly possible. Also, cost simulation needs have to be considered during the early phases of the space systems engineering, while eliciting the requirements and performing the architectural design of the system models during the MBSE process. In this regard, a model-based approach was used in ACOSIM to demonstrate concepts of how the system-level architecture can be mapped down to a simulation architecture and how a formal model can be used to derive simulation-related information. In this slide, we can see the approach followed in the project, which has 4 steps. Firstly, we analyzed cost simulation tools and methods used outside the space domain in order to identify the best practices that are already in place and not to reinvent the wheel. In this analysis, major focus was given to the FMI standard widely adopted in the automotive sector. The second step was to analyze previous work done in the space domain, where a variety of standards, projects, reference architectures, tools and methods have been considered. In the third step, we defined a new verification and validation methodology using cost simulation, with particular focus on design, software, and operations verification and validation. And as a last step, the methodology was demonstrated in 3 different proof of concepts, each one targeting a system simulation facility. For the system-level modeling, the Capella open-source tool developed by Thalys Alenia Space has been used. Capella implements Arcadia, a system engineering method based on the use of an MBSE model. Without loss of generality, only 3 disciplines were taken into account for the ACOSIM demonstrator: the GNC, thermal, and electrical power management. In the Arcadia method, the logical architecture defines the functions, the exchanges between the functions, and the allocation to each logical component. This is the starting point for the definition of the spacecraft physical architecture, but at the same time can also be used for the functional engineering simulator. The physical architecture defines the hardware-software implementation. Mapping between logical components and hardware-software implementation provides the input for the mapping between the FES and the SVF in terms of control functions implemented by software or other means. The SVF is mapped to the physical architectures and so indirectly also to the logical architecture, so to be able to analyze the transition between FES and SVF simulators. The SVF and the FES can be enhanced through bottom-up approach to cover also other cases such as AIV and TOM's needs. To bridge the gap between the system modeling and the system repository with respect to the simulation metamodel, an automated procedure was implemented within ACOSIM by TVT. The program analyzes the system architecture and design as modeled in Capella and detects possible design changes that would lead to invalid data links and interfaces between the simulation models taking part in the co-simulation setup. For dependencies management, the SADM tool developed in the new modeling methods ISA project was used and interfaced with Capella tool. Next to the dependency tracing, it is also shown that an automated initialization of the co-simulation setup becomes feasible via the generation of an FMI model description file derived from the Capella model. The consortium is currently implementing the end-to-end concept with main principle to validate and enhance the proposed co-simulation verification and validation methodology. In this regard, the functional HUBCAP interface has been explored as a candidate for facilitating the co-simulation. The advantages as known from the non-space sector when it comes to FMI-based co-simulations are easy exchange of components and models, IP protection mechanisms, gaining robustness in the workflows, and coupling possibilities of different domains and tools. In the first ACOSIM proof of concept, the thermal and power discipline models as generated for the FES in MATLAB Simulink tool, as well as a C++ GNC model, have been exported as FMI-compliant models, and the underlying FES scenario was executed as an FMI-based co-simulation. For the execution purposes, the IntoCPS co-simulation orchestration engine, developed by Aarhus University, was used as the software controlling the simulation execution. The second proof of concept of ACOSIM concerns the co-simulation of models coming from a FES simulator and models developed in a software validation facility. For the demonstrator, the Eagle Eye avionics test bench has been used as the SVF environment, and its pre-existing SMP2 thermal and power models have been interfaced with the FMI counterparts originating from FES and Proof of Concept 1. In this setup, all the calculations are performed inside the FMI models, and their results are transferred to the relevant SMP2 models. In order for the SMP2 models to be possible to access the FMU models and retrieve their results, a software enabler called Maestro Connector has been developed by MTech. The enabler facilitates the communication between the SMP2 models and the FMI orchestration engine. The third ACOSIM demonstrator aims to connect models from three different simulation facilities: a gyro model residing in a SVF, power and thermal models coming from a FES environment, and a TOMS simulator being the overall master of the co-simulation. To achieve this, SimBridge tool developed by MTech has been used to interface the Simulus tool used by ESA for all operational simulators with an SVF based on Eurosim. Via this connection, the logic of a gyro model is running on the SVF environment, while its results are passing through SimBridge to the actual model residing in Simulus. On the other hand, to communicate with the FMU models coming from FES, an FMI adapter was implemented within Simulus as an SMP2 service, giving to the SMP2 models access to their FMI counterparts. In this way, higher fidelity models coming from previous phases of the project, such as FES and SVF simulators, can be easily exploited within the operational simulator, promoting the vertical reuse of simulation models. To sum up, the ACOSIM study aims to define a new verification and validation methodology using co-simulation. The study investigated the role of co-simulation in the space domain with focus on the FMI standard. An MBSE approach was used as the enabler to promote co-simulation from the early phases of a space project. 3 proof of concepts have been developed to demonstrate co-simulation between 3 different system simulation facilities and including 3 engineering disciplines. 4 software enablers of co-simulation have been developed, which can result as starting point for future ESA co-simulation projects. Thank you very much for your attention. I will now pass the floor to Professor Peter Gorm Larsen, and I will gladly answer any question regarding ACOSIM in the end of the presentation.
My name is Peter Gorm Larsen, and I'm a professor at Aarhus University. I'm here today to talk to you about the HUBCAP project, which I'm the coordinator of. We have 17 partners, and the people here have been involved in writing the abstract for this. HUBCAP is about trying to develop an online model-based system engineering collaboration platform, and it includes the co-simulation Maestro into CPS things that you have just seen in the first part, because we have also been involved, Aarhus University have also been involved in the ACOSIM project. So HUBCAP is an innovation action. It's financed by the Horizon 2020 program with roughly 8 million euros. But the point here is to have a vision of trying to lower the barrier for SMEs to realize the potential that are there by using model-based design in general. We have a network of digital innovation hubs, and we have a number of small and medium enterprises that are filling up things into this platform. And the platform I will try to demonstrate to you and how it supports model-based design. And we also have open calls where we are giving away funding for SMEs to actually add things to the platform, as well as try out things in the platform. These open calls are having 3 different kinds of natures. The first one is one where people are putting in assets and getting a small fixed amount of money for that to help with filling up the platform. And then the second one is about doing experiments. And the third one is trying to innovate further. And these calls are coming later in the project. This project started 1st of January, so we're not so far yet. But we should have some results to show. And I would like to indicate to you how we try to limit the initial investment for newcomers to get into things using what we call a sandbox capability. Particularly when we have SMEs, then they typically collaborate closely together with larger organizations. And I suppose the same thing is true in a space sector, where getting started with paying licenses can be quite expensive for the different tools that you would like to use. So the idea here is to try to pay as you go rather than paying license per seats. And then we would like to get SMEs started with their first projects using this model-based design thing, and we will support it by means of the digital innovation hubs, giving them training, etc., and helping them. So the initial investment is then lowered as well because of these open calls, where up to 70% of the expenses can actually be covered like this. And therefore, we hope that also some of you in the space sector would be interested in trying to use this. So here we have a tools catalog where you have different tools that have been put into the collaboration platform. We also have a models catalog, which are putting in models that can be used as starting points for your development. And this could also be models in a space context. But the unique innovation in this project is the sandbox capability, which enables interaction between tool providers and users, and it's essentially have it ready to go rather than downloading something to try, having to make sure it works for the right operating system and its dependencies in terms of Java or Python or whatever. And then essentially each sandbox contains a number of things that have been put into it, and they each are separately in their own virtual image, and they're connected by a virtual LAN, and thereby we have a possibility of trying out combinations of things and also to collaborate. So let me try to demonstrate the key functionality here in two videos. So the first setup here is trying to illustrate we have operating systems, and these are the normal ones, and we have tools where the different tools are being added as we speak, and we have models, and there are more models now than when the video here was taken. So in order to illustrate this, we are trying to demonstrate here first, trying to add the Into-CPS tool suite that you have heard about in the first presentation. We're also adding Overture, which is also being maintained by the Aarhus University team. And we are adding one of the tutorials with a couple of water tanks coupled together inside the same setting. So we're now starting up a sandbox, and it's having its own network. And essentially, these are, tailor-made virtual images that contains exactly the tools and the model we have asked for here, and the configuration is then enabling you to operate these different ones, log into each of these images, and then be able to operate with them without downloading anything. This is all from your browser. So you see here the two, here's the Overture one, and for each of these are virtual machines, so we would log into them. And my colleague Hugo is doing that right now. This is being demonstrated in parallel to the presentation track here. So in case you're interested in seeing your own demo, you can go there as well. And you can see when you log in, you actually have the tools installed. So here's the Into-CPS tool. Now let me try to move on to the next video here. The next video here, we have started up the tools. We're now trying to configure a co-simulation, and in this case the configuration has been set up. You see here you both have the kind of graphs as you shown on the left hand side, and also visual animations on the right hand side with these water tanks connected and the water pouring in and out depending upon the state of the valves included in here. In this particular case, the controller is made using this Overture tool in VDM, and the continuous time modeling had been done in a tool called SvendeSim that also have been used in different settings with the European Space Agency. But the point here is that we have access to different tools directly from the web, and we can try to experiment with the consequences of different things. In this case, we have just taken in two images, two tools, and we have taken in a model, in this case a model used for a particular tutorial. I talked also about the collaboration, and what you see on the right hand side where it says invite as guests is actually a possibility of doing that. So now Prasad have been added as an active guest over here. So he means he can see exactly the same sandbox. And you can see he's the owner and he's the guest of someone. And this means that you can actually have multiple people working on the same sandbox instantiation in parallel. It means you can work together. And I think that this could be quite valuable also in a space setting where you have typically consortiums of people who needs to collaborate. And this FMI standard we're using enable you to have black box things, so it is possible to save your own things and not having to work with see the details of your give you details to your collaborators. So to give a few concluding remarks, I have talked about the HUBCAP project. I hope that you have some impression of what it is. There are open calls for SMEs from Europe, from EU, who are interested in this model-based design. In case you are an SME, I definitely encourage you to look at these possibilities. And then I have demonstrated to you this cloud-based collaboration platform for the model-based design of cyber-physical systems. It's possible to see our web pages, follow us on Twitter and LinkedIn. So I hope that you would like to get further with this kind of technology. So in case you have any questions, I'm very interested in hearing them. Thanks.